In this video, we're going to talk about limits and continuity. So just to refresh our memories about continuous, if we're looking to see if our function is continuous at a point, we'll call it C, then these three things must be true. F of x has to be defined at C. In other words, for that x value, there's a corresponding y value that's actually defined. The second thing is that the limit as you approach that C value of your function exists. In other words, the left and right hand limits approach the same value. And the third qualification is that the limit as you approach C and the value of y at C must also be equivalent to each other. That's the basic definition of continuity at a point. We also have three basic types of discontinuities. We have removable, jump, and infinite. So to look at a removable discontinuity, it's like you have the entire function, but you're missing a single point. Like so. So if this is my C value, I'm missing a point. It's like I removed one single y value out of the entire function. A jump discontinuity, if you look up here in the top right, it's like your function jumps from one y value to a completely different one. It's not smooth. This typically happens with piecewise functions, but that's your jump. And this is also called a gap discontinuity as well. And lastly, an infinite discontinuity is when I'm at my point C, if both or one of the sides of my limit are going to infinity or negative infinity, then we say that it's an infinite discontinuity. So next we have some basic limit laws. Basic laws of continuity. So if we have got two functions that are individually continuous at a particular point, x equals c, then the following functions are also going to be continuous. So the first thing is that if we have a sum or a difference of those two functions, they'll also be continuous. If we have a scalar in front of one of our functions, so 2 times f of x, 5 times f of x, then that will also be continuous as well. If we take those two functions and multiply them together in number 3, that function, its product, will also be continuous. And last but not least, if we have the quotient of the two, it will be continuous as long as g of c is not 0, because we divide by 0, math explodes. Next, we're going to talk about the continuity of polynomial and rational functions. So let's let p of x and q of x be polynomial functions. So p of x is continuous on the real line. That just means not imaginary. So if you have a polynomial function, no matter what it is, it will always be continuous no matter what, which is really nice to know going into your problems. The second thing is if we have a rational function, if we have a fraction, it's continuous on its domain. In other words, it's continuous everywhere except where q of x, or the denominator, is equal to 0. So, for example, here we have a quotient of x squared plus 5 divided by x minus 4. So we want to ask ourselves, where is the denominator actually equal to 0? And to do this the long way, just to make sure, we set this denominator equal to 0 to see where that happens. We solve, and I get x equals 4. So what that tells me is, first of all, my domain is everything except x equals 4, and so is its continuity. So that's how you have to figure out the continuous parts of a rational function. Okay, so there are actually some basic functions that we can discover the continuity of it pretty quickly if we know some rules. So the first one is if we have y equals to x to the 1 over n. In other words, if it's to the 1/2, 1/3, 1/4. In other words, like square root, cube root, fourth root, etc. So the way to find the continuity of one of these functions is it's just continuous on its domain as long as n is a natural number. So 1, 2, 3, 4, 5, it's like you're counting numbers. It doesn't really work for negatives. You want to just make sure that you know the domain of that function. As long as you know the domain, then that function is continuous on that domain. As for your sinusoidal functions, your sine and cosine functions for sure are continuous everywhere. It's your basic sinusoidal function. It's just, it's your periodic up and down movement. It's continuous everywhere. The next one is an exponential function. So exponential functions are going to be continuous everywhere as long as your as long as your base b is not 0, and as long as it's also not 1. So if you have every other condition besides those two things, then you're good to go. It's continuous everywhere. And last but not least, if we have a logarithmic function, it's going to be continuous everywhere as long as x is greater than 0. This has the same conditions as exponential functions, since these guys are inverses and they have to kind of have the same properties. So this condition, this b has to be greater than 0 and not equal to 1, also has to pertain to be true. So if you know your basic function domains and a little bit about them, you can easily find out their continuity as well. And let's not forget either that if we have any two of these particular functions, especially like sine or cosine, if we do its product, sum or difference, quotient, remember that based off of this previous page right here, that because of your basic continuity laws, those will also be continuous. So you just have to watch out for the domains and the kinds of functions that you have. So next we're going to talk about the continuity of inverse functions. So let's say we have our function f of x and it's continuous on a specific interval. We'll call it I. And it has a range, we'll call it r. And if the inverse of that function actually exists, then the inverse function is continuous with the domain R. And this should be understandable simply because inverse functions have the domains and ranges switched. So the inverse function is going to have the continuity on the domain of the range of my original function. So that's just what you have to look for inverses. So another type of function that we're going to talk about its continuity with is composite functions. So for the composite functions, if we have a function g, and if it's continuous at x equals c, so some point, and f is continuous at x equals g of c, then the composition is also continuous at that point. So let's take a look at an example of this. So I'm going to have f of x equals x squared plus 1, g of x equals x minus 3, and we're going to take a look at the continuity of the composition of these two functions at c equals 5. So we have to take a look at the first part of our criteria. It says if g is continuous at x equals c. First of all, identify this kind of function. This is polynomial. It's also linear, but it's a polynomial function, and we learned in this video that polynomial functions are continuous everywhere. So this function is continuous at c equals 5. The next part is that f is continuous at x equals g of c. Well, I haven't done that part yet, so let's go ahead and figure out what g of c actually is. So I'm going to do g of 5, which is 5 minus 3, which is equal to 2. So the x value for my f function is now going to be 2. That's what this part right here is telling you. So I'm going to use x equals 2 for this particular function. So our function f has to also be continuous at this particular point. So far this one checks off at c equals 5. Does f check off at x equals 2? And of course it does, because this is yet again a polynomial function. So they both work. Therefore, the composition of the two, this guy right here, will also be continuous at that point. That's what that rule says for continuity of composite functions. So with that being said, we have one last thing to talk about. We have to talk about elementary functions and what the continuity for those are as well. So elementary functions are constructed out of basic functions, so the ones that we just looked at, using addition, subtraction, multiplication, and division, and composition. So what we know about the continuity of elementary functions is that they actually are continuous on their domains. So it really doesn't even matter how complicated an elementary function can look. As long as you know how to find their domains, you know how they're continuous. Here's an example. So let's take this big function as an example. There's a lot of things going on here. We're going to try to figure out the domains of all of the individual parts first and kind of figure out how that influences the continuity of it. So the tangent function in itself is the one that kind of looks like this, right? It's got all these asymptotes all over the place. Now, the range of that function is all real numbers, so the inverse of that, which is what we have here, is the range of that particular function. So this guy is actually continuous on all of the x's that are equivalent to that range, which is everything. So this guy's domain is all real numbers. When I take a look at x squared, that's polynomial. That's also all reals. Here I have a cosine function, and it doesn't even really matter what's happening inside. It's still a cosine function. This is also all reals. The only part that's actually going to affect our continuity is our denominator, because we know that a denominator can never be equal to 0. So this function is continuous everywhere except where that is 0. In other words, when x is equal to positive 8. That's really all you have to look for. If you know the continuity of your basic functions, it doesn't matter how complicated the elementary ones can get, as long as you know how to find the continuity of each individual part. And that will conclude this tutorial.